Hi everyone, and welcome to this partner webinar, which is on Boost Your Edge AI development with Zephyr and TFLite Micro. Today, we are very excited to have Antmicro with us. They will present their simulation framework, Renode. They will tell us how Renode is related to Zephyr and TensorFlow Lite Micro, and demonstrate how you can use it to emulate the popular nRF52840 SoC in different scenarios and use cases. Just some practicalities before we get started with the webinar. The expected duration of the webinar is around an hour. Questions of course, highly encouraged, and you can ask your questions by typing them in the Ask a Question box, which is located at the top of the right sidebar. All questions are anonymous. Please try to keep them as relevant as possible to the topic. We will answer these questions towards the end of the webinar. Please note that the chat, which is at the bottom of the right sidebar, that's not anonymous, and please avoid using it to ask questions. If you have more questions, feel free to visit Nordic Semiconductor Dev Zone, where we have a team of engineers and developers that are very eager to help you. And for questions related to Antmicro, you can visit antmicro.com/about/contact. Note that a recording of this webinar along with the presentation will be available at webinars.nordicsemi.com. So my name is Ali Aljani. I'm a product marketing engineer with Nordic Semiconductor, and from Antmicro, we have Piotr Hofer. He's an engineering manager at Antmicro. Piotr, could you please introduce yourself and take it from there?
Hello, thank you very much for inviting me. My name is Piotr Hofer, and I am an engineering manager at Antmicro. And I'm here to say a few words about ways in which you can improve your embedded development. First, let me introduce you to Antmicro. Our company was founded 12 years ago. We're an open source company providing engineering services in everything embedded. We work on bringing innovation into how people create embedded systems. And we provide our services in various high-tech fields like automotive, defense, security, robotics, aerospace, industrial automation, etc. We focus on the whole stack of embedded systems development, from hardware designs, ASICs, through FPGA, software development, through tooling, edge AI to cloud services. And Antmicro is very much focused on open source. We support and develop a range of open source solutions, even in the fields that are not traditionally open, like hardware design, but we try to open them anyway. We are members of various open source initiatives. We are actively involved in them as well, like Zephyr, like Linux Foundation, but also RISC-V, CHIPS, or Open Power. And today I would like to tell you about the project I'm leading at Antmicro and with which I'm involved from almost the very beginning, which is Renode. I will introduce you to Renode itself, and I will try to show you how do we use it in the context of our engagement with Zephyr and TensorFlow Lite Micro. So, what is Renode? Renode is a simulation framework. It's open source, it's software agnostic. It supports various architectures like ARM Cortex-A, Cortex-M, RISC-V, Power, Spark, etc. It allows you to create complex embedded environments and run exactly same software you'd normally run on your hardware. So there is no need to compile specifically for Renode. To do that, we model actual SoCs and boards and all of the AP so that they mimic the reality. In its core, Renode is an instruction set simulator, providing you with full determinism of execution, tons of cool features helping you with debugging, tracing, and is also very well suited for automated tests and being integrated in a CI system. As I mentioned, Renode is software agnostic, so it can run either bare metal software or an RTOS or Linux or whatever you choose to load in it. While there is no requirement to run anything specific, Renode has extensive insight in the execution of your software. So if you want to make it aware on your software-specific features, you can do that. And we have run plenty of different payloads. The list here is not at all exhaustive, but our users always surprise us with even more, so that's pretty fun. Renode is focused on this idea of building blocks, so we can go as low as just simulating bare CPU to verify your machine code in the application that you load, or you can simulate a complex SoC with all the peripherals and whatnot, or even a board with all the sensors, inputs, outputs, like the display, for example. Or you can go even further and have a multi-node system with wired or wireless connection, running fully deterministically in a single simulation environment. So this is basically our point, that we don't want you to work with a subset of your application's functionality in Renode and have to test a lot on hardware anyway. We'd like you to be able to recreate almost everything in a purely virtual setup. And Renode has been used in oh so many different areas. Some of them were in our heads from the very beginning. Some of them were just invented by users, which is super cool. So this list here is also not really complete in any way. So Renode is very well suited for classic software development for IoT or any kind of embedded system when you don't want to spend too much time with hardware. But it can also enable you to start programming even if you don't have the hardware yet. Or you're even just looking for a proper architecture of your future product. CI I already mentioned, and TinyML is a really big thing for us right now. So there's just a never-ending list of ways in which you can use Renode. Whenever you need to be able to actually inspect what's happening inside your solution or need to test things thoroughly, which we believe is always, Renode is your tool. So I assume that most of the audience already knows what Zephyr is. It's a super popular RTOS, which we are heavily involved with. Very recently it got its second long-term support release, 2.7, so congrats to everyone involved. That's very exciting. And while we have experience with various different RTOSes, Zephyr is definitely the modern solution of choice for us nowadays. We're a platinum member of the project, we contribute to Zephyr, we promote Zephyr, we use Zephyr in our projects a lot. Renode is actually used by Zephyr's testing system called Twister, and you can see some logs here from one of the latest runs of Zephyr CI. And our goal is to have a wide range of boards supported by Zephyr to be tested in Renode on each and every commit to main, which is definitely easier and more effective than doing the same on real hardware, which is actually impossible. One of our experiments to see how much of Zephyr can we run in Renode is the Zephyr dashboard we created very recently. In Renode, we often use Zephyr to prepare tests or demos of different hardware that we support, and right now we have about 16 different virtual platforms that by default run Zephyr. So with this idea that hardware is very often quite similar and silicon vendors obviously reuse IP in their products, and with the fact that Zephyr provides device trees for all of its boards, we wanted to see how many different platforms will we be able to start in Renode to run Zephyr Shell, which is a nice self-contained example that already tests several things like interrupts, serial initialization, etc. So we created some scripting, some mapping of building blocks, and right now, out of the about 400 different boards supported in Zephyr, we are able to run 94, which I believe is a pretty nice number and proves the point. Keep in mind, it does not mean that we support 94 boards from Zephyr in Renode, but we support similar hardware, and getting from the one we have to the one we need is sometimes not that very difficult. So I'll show it in practice in just a second, but let's jump to the second target of this presentation, that is TensorFlow Lite Micro. So here we start with the concept of tiny machine learning. It's machine learning that you don't want to run in the cloud, far from your data source, but you want to run immediately after you get data, for example, from a sensor. This is crucial for real-time applications, and the word tiny in the name means that we want to run on very constrained devices. Of course, small devices are not very powerful, but they are everywhere and we have a lot of them. And it turns out that to do proper TinyML, you don't need much. You need to be able to run calculations, to run your code. You need to have data, so maybe some sensors, maybe just one or more. You need to have some way to report your results, so network or serial or maybe a trapdoor trigger or some explosive device, whatever. And that's pretty it. So there are not many requirements to run TinyML. And TFLite Micro, a little brother of the very well-known TensorFlow project, is designed to support exactly that. Running machine learning algorithms on very small platforms that are not necessarily designed with ML in mind, but they do have some compute and can provide meaningful and actually useful results. TFLite Micro is an interpreter. It relies on similar models as TFLite, which you'd normally find running on your phones, for example. And it's cross-platform, which means it requires a HAL to run on hardware. One of our projects we did for the TFLite team was to provide a Zephyr-based build target. And of course, we implemented that with support from Renode. As we did already support the target platform, we used to run Zephyr on it, so it was very helpful in the process of development. This was later on pushed a step further by Intel, and now TFLite Micro can be used as a module for Zephyr, which is pretty cool. So enough of me talking. Let's see how can it all work in practice in Renode. I will have a few demos to give you a very brief feeling of what Renode is and what can be done. But there's always more that I won't be able to show. So I invite you to ask questions and to visit our website and stay in touch. So, this is Renode. Renode is an API-based tool. There are dozens of ways you can interact with it, but the most basic one and the default one is our CLI we call the monitor. It allows you to enter commands and control the whole emulation with them. So let's start by loading our default NRF52840 demo. Obviously with Zephyr shell running on it. I type in the command that loads a script which consists of similar commands that creates machine, loads the ELF file, etc., etc. So now you see a new window popped up, and this is the window for one of the UARTs. So let's just start. And yeah, you see a prompt of Zephyr shell, which is not extremely impressive, but it's interactive, and you can play with it. You can see we're running a fairly old Zephyr version. You can see something in red in the background, but that just means that we don't implement each and every building block of this SoC, but that's fine. It doesn't really affect this emulation here. Of course, there's so much more you can do with your emulation in Renode. First of all, you can access each and every peripheral that's available. So here I typed in the command peripherals, and I get a list of all the building blocks that are here. You can inspect and change their state. Let's type in the name of the UART, and here you have access to all the properties and functions and methods that are available in the model. You can call them and change values and read values, etc. As I mentioned before, Renode gives you a lot of nice introspection features. So, for example, let us see how does your software interact with the UART that we have here. So let's log all accesses that are happening on this UART. Let's type something in. Hello. So in the log, you can see that there are many entries regarding accesses to the UART. So UART is being written to or read from specific registers with specific values, etc. So this is a very useful tool if you're creating a driver and you want to debug it and something's working not as you'd expect. You can easily spot what accesses are actually being executed by your core. But admittedly, this information does not have a lot of context. We can provide this context by logging function names that are being executed by software. Not by Renode itself, but by the software that we run in Renode. So here you can see that we'll be logging functions that begin with the UART or UART E prefix. And these happen to be Zephyr driver functions for the NRF 52840 that control the UART. So let me type something in. Hello world. And you can see that now not only do we have the accesses listed, but we also know in what context they were executed. So it's a very nice tool to debug your software and actually understand what's happening inside. So this was obviously a fairly trivial example of how to use Renode, but Renode is also very well versed in working with tools you're familiar with from your everyday work, for debugging software, for network traffic analysis, for everything you can come up with. And GDB is the obvious thing here. You can use GDB the same way you'd use it with the actual hardware, and you can have all these standard features like breakpoints, watch points, accessing memory, whatnot. And the nice thing about debugging in Renode is that it can be absolutely transparent to your software, because whenever you break in GDB, we hold time for the entire emulation. And this is extremely useful in multi-node scenarios if you have some network communication going on. It simply does not time out when you're stepping over your code, because we control the time flow for each and every machine. And for IoT development, this is invaluable.
So let's see some interactive debugging in action. First, let me start Renode. I have a binary that is prepared specifically for this test, so let me just load it. It's a modified Hello World Zephyr application, and let me just load the platform. So what I need to do to be able to connect with GDB is to run machine start GDB server on a specific port. And from now on, we'll be only interested in this UART window and the GDB window. So I will run GDB from the Zephyr SDK, and I will connect to my remote machine the usual way. So target, remote, and the port number. And what can we do here? We can do all the usual stuff, as I mentioned. So let me create a breakpoint on main. I can also control Renode from GDB using the monitor command. So monitor start to run the emulation and continue the GDB itself. Okay, so yeah, we are in a breakpoint. We can see the code. It's not very complex. You can see that we have a variable that's 0. We are printing something out. We are increasing the variable, and then we're printing something else again with the value of this variable. The secret is that it will print out, hey there, 1. It's not really a secret, but let me step over the code. So yeah, it should print the hello world right now. As you can see, it appears on the UART. I should be able to print the value. PI, yes, I can do that. I can step over. It should be increased. And now I will change it because I can do that as well. So set variable I to 1, 2, 3, 4, 5, let's say. I can also look up registers of the CPU, and I can do all the usual things. I can do watch points, etc. So let's go next. And yeah, I can see that we see header 1, 2, 3, 4, 5. This is of course a usual thing that you see in GDB, but combine it with our multi-node capabilities and all the introspection you can do from Renode Monitor, and you receive a pretty powerful tool that allows you to do really nice debugging that does not influence the debugged application in any way, which is, I believe, quite important.
But speaking about multi-node, I mentioned before that we focus on this a lot, and I have the pleasure to show you the very first demo of our Bluetooth low energy support in Renode running on NRF52840. This was in progress for quite some time, and the development was actually supported by a member of the community, which makes us super happy. And this is not yet in upstream Renode, but should be there in a couple of weeks. So what you're going to see is still a work in progress, but let's have a quick demo.
Let's start the first BLE demo, but maybe first let me show you what does a script look like. This is the multi-node script for the BLE that we have, and it's actually very simple to combine two machines in a single setup. First, we create the wireless medium. We create the machines. We load the ELF files. We open the UART window, and then we do the same for the second one. And we set the quantum illumination, which is a bit of a internal knob to turn that allows you to receive faster results. So let me start it. Renode. I load the script. Yeah, and I get two windows, one for peripheral, one for central node. And let us just start. Some initial printouts on the UARTs. And yeah, it's already we received some first heart rates being sent and received on the central node. But wouldn't it actually be quite nice to see the actual communication? So when you try to observe the communication between BLE nodes in real life, it requires you to add a third machine that will just be a sniffer of the traffic. And of course you can't sniff everything, and you sniff also all the other traffic that's in your room, for example, in which you work. Let me start the very well-known application that you should probably all recognize, that is Wireshark. Wireshark is a great network traffic analyzer, and yeah, you can, with no additional configuration, you will be able to see that the packets are being transmitted between the nodes. So here are just empty keep alive messages. But here you also see that there are some actual protocol messages being sent. 06 is the constant value that is being also always sent, and 61, I believe, is 97 in hex. So yeah, this is something that you can set up pretty easily. There are some other nice features of our wireless support. For example, you can add additional constraints on the range of the medium and on the radios, so that when they exceed the maximum range, they just start dropping packets, either completely on in a stochastic way, or you can create your own delivery function that will run your specific math to calculate if the packet was delivered and if the packet was successfully received. So yeah, we're pretty happy about this. We hope to release it soon. As I mentioned, this is not yet publicly available, but should be there in a few weeks.
Quite a few times did I mention testing and CI, and there are multiple ways you can use Renode for testing. Our standard way is to use the robot framework. It's a generic Python tool for writing, running tests, and for getting reports. It allows you to write these tests in more or less English using predefined keywords. And we provide such keywords for various different things. You can inspect UARTs, network traffic, you can inspect logs, memory, CPU registers, etc., etc. So let's see such run in practice.
To make it quick, I will just run a single test from our nRF52840 suite, and let's make it the BLE test. First of all, let me open the test file. It contains all the tests we have for this platform. Let me just straight to BLE. So what does it do? First of all, it creates a central machine. It loads the specific platform description. It loads the required binary and connects to the wireless network. Then we have a second machine that follows the same suite but just uses a different ELF file. So after we have the whole setup prepared, we see a line of verification tests that check if the specific output on UART was received. So first of all, we want the machines to boot up. We want Bluetooth to initialize on both machines, scanning, connection from central and peripheral, and at the very end we want the central node to notify that the peripheral has subscribed and that it sent its first notification. So let's run it. Here I provide the test file and just filter out a single test. So as you can see, Renode is already started by the script on a specific port. We connect to it automatically. You can see the name of the test being printed out. And you can, of course, run multiple tests in the same run, just providing them in a list of tests in a YAM file. So here we see that several interesting files were created. Let me open the report. Here you can see the list of tests that were being run. And of course, it's only a single one in the specific instance. But we can enter details and we see a nice list of keywords that are being run in this specific test along with the results. Of course, everything passed. But this is makes things very easy to spot where the error happens. As these passing tests are not that interesting, let me run a test that will deliberately fail. That's why I changed BLE to ELB, because the test has a typo in it. Running tests in Renode, apart from giving you this easy to analyze results and nice reports, allows you several other things. For example, we create a save file of the whole emulation. So we have a single file that contains all the binaries, platform files, scripts. Technically, it does not contain scripts. It just contains the specific state of the simulation that you can either load yourself or send to someone. So yeah, here we see that there is a report of a failed test. We see that a log was saved. We see that the save file was saved as well. So these are usual artifacts of a test run. So open the report file. We see the information that the test failed. And when we go to the sample, here's the summary of the test, but we can also see each and every keyword. And yeah, this one failed. It was waiting for the string surcrisp to be printed out, which didn't happen, of course, because it was subscribed that was printed out and not this one.
With all the automation that we have, keeping in mind, of course, that it's a great tool for interactive work, we believe that Renode shines especially in CI environments. In the modern software development, testing is an obvious thing. And we think that in the embedded landscape, it's not valued enough. Things go very often under-tested, and because of that, they have lower quality. The only way to solve it is to test constantly on each and every commit. But of course, this is difficult if you have, for example, an IoT system with dozens of nodes that you have to deploy in the field. And that's where Renode helps a lot. So we've been collaborating with the TFLite Micro team for quite some time now. And one of the goals was to ensure that TFLite Micro is properly tested. Renode was part of their CI for a very long time, but only on the basic level running unit tests, which is also very important, but does not cover everything. Now we wanted to cover a much broader scope, running the same applications a user would run on their hardware. And quite a few interesting things were born during this cooperation. First of all, we created a dedicated GitHub action to allow users to run their tests in Renode with as little effort as possible. You can find an example project that's based on, obviously, NRF 52840, and that uses this action on our GitHub. And it's a complete setup showing how to create an end-to-end CI in your repository. It's fairly trivial. The whole test workflow is visible in the slide. And if you look very closely, the whole process of setting up Renode and running tests from your robot file is in lines 20 to 24. It just says use the latest Renode to run my robot test. And you get the results report similar to the one I just showed you. And so this was pretty basic, but the big thing that we worked on that also uses this action is the test repository we created for Arduino Nano 33 BLE Sense board with NRF 52840 and a ton of sensors available. In TFLite Micro, this board supports 4 scenarios. Simple hello world, magic wand analyzing an accelerometer input, micro speech for detecting audio keywords, and person detection using input from camera. Of course, we modeled all of these inputs, and thanks to that, we have an end-to-end test flow, testing the whole software exactly as it would run on hardware, so including drivers, without any mocked data. And this type of comprehensive tests is what we believe to be the most reasonable way to verify complex software. And of course, machine learning software is extremely complex. You can find a repo with this test on our GitHub, but I also want to show you some more, let's say, visually appealing things we created with the TFLite team that would conclude my today's presentation. Let's start with Google Colab notebooks. You can find links to our notebooks in the repo from the previous slide. Colab is a service that hosts and runs Jupyter notebooks in Google Cloud. And Jupyter notebooks is simply a document format that can contain runnable code. And we wanted to see if it would be able to run Renode. And actually, yes, it can. I already pre-ran parts of this scenario, so the script downloaded Renode and TFLite Micro binaries, and now we have to provide some input and run the machine learning. You can provide data from your camera or just use something predefined, and I will stick to that as I don't want to not be recognized as a person. Because, yeah, as you might guess, this scenario is about person detection. So yeah, let's run it. We'll by default we're using some predefined image. It gets auto-scaled to our preferred size, and then we can see some script that talks to Renode. And you can actually see an output from the UART, and you can see that this person was recognized on this image. What more? You can see some interesting metrics gathered during the execution, and this is also available in your local runs.
For example, here we have a graph of executed instructions over virtual time. So you see that for the most time the core mostly sleeps and it just executes computation in some specific period. You can also see accesses to memory, reads and writes. You can see access certain exceptions being executed by the CPU, and you can also see accesses to different peripherals in your board. So this gives you, along with other features that we have for introspection, it gives you a pretty nice view of what's actually happening in your machine learning application. As a cherry on top, I would like to show you some UI work with it to make it more tangible. So let me run Renode and start the visualization server and open the web page. So this is Arduino Nano, of course with Nordic chip, and as you can hopefully see, a ton of sensors marked here with the circles. Even with the ArduCam camera that we support in Renode. And here I'm running a trivial blinky example, and yeah, hey, it's alive, it blinks. This is served directly by Renode, so no additional tools are required, and we think that it's a nice way to see that your virtual platform actually represents physical hardware. And you can see it, you can use it for demonstration purposes or in your everyday work, just to play with sensors and actually see the effects of your work.
So, summing up, if you want to see your software as alive as our Blinky, and you want to test properly without the hassle of creating complicated hardware rigs, use Renode. It's open source, you can give it a try, let us know what you think. Here you have some links to the materials on Renode. So our main web page, nightly builds for Linux, macOS, and Windows, documentation, and of course our GitHub. We as Antmicro also offer services around Renode, so feel free to reach out if you're interested. And let's talk more about projects you might have that Renode could help you with. And yeah, thank you very much for your attention. Thank you to Nordic for having us here. And I would be very happy to answer any questions you might have. Thank you very much.